Okay, in this video, we're going to have to get technical. I hate to go ahead and break that news to you, but I might as well because I need to get the bad news out of the way first. So if you thought the other lecture videos were like detailed and oh my gosh, he's going to be so crazy-fied when it comes to pH probes, what's he going to be like for the rest of the semester? Well, this is just how the pH is, and it's things that people take for granted, and I think it's important for you to understand what's really going on at the surface of the probe in this case, because if you don't understand the workings of a pH meter, how are you going to take care of one when you go out and you work in a lab? So a couple of things that we have talked about in the previous videos were really terms, but actually more than that, they were actually things that we defined, but things that we drew and things that we discussed on kind of what's going on the inside of them. So the first one was the ISE, which is the ion selective electrode. And we said that was the measuring electrode. That's what's actually looking at your hydrogen concentration that will be in your solution to figure out how much is there, and that corresponds to the pH readout that we'll eventually discuss. The next one was the external reference electrode, and we said, well, that kind of gives this thing a constant value to compare itself to, but it also serves as the salt bridge. So that's where the porous disc is, and that allows for the completion of the circuit that we're talking about in the pH meter. And then we also talked about what goes on in the inside. So both of these, the ISE and ERE, have silver wires, and both of these have chloride solutions in each chamber. In one version, it's silver chloride with a little bit of acid. In the other version, it's potassium chloride that they are using for the filling solution. And then, because it does have a concentration of HCl to help dissolve up that silver chloride, that's even better, folks, because what that's going to do is give me hydrogen concentration that we can also use when we talk about the sol gel layer and what is going on activity-wise at the end of that measuring probe. And that's what this lecture is going to be about. All right, so I want to start by drawing the end of the ISE again. All right, so this is the end of the probe that we have calibrated maybe up to this point. We've not really talked about that yet, right? But this is the ISE. And we said the ISE, yet again, has this like jelly sol gel layer on the surface of the probe. So we said that that sol gel layer is jelly-like. We said that it's meant like a piece of lattice in a way. It gives us this nice little kind of structure, but not too structured. But it gives us this grid network that we can use. And that sol gel layer is made up of 25% sodium. Okay, and we discussed a little bit, well, you know, there's sodium in here, right? It fits in that area quite nicely. And then sometimes it'll boop, come out. That releases an opening. And sooner or later, if we've got hydrogen that's in the system or in the solution, because keep in mind, this whole thing is in the solution, that hydrogen can see that opening and say, oh, all right, I'm going to move in. That was also discussed in a previous video. Now I want to go even deeper. That's right. You're probably thinking to yourself, oh my God, how far is it going to go? I mean, is this going to be a whole class on pH? I know, I'm almost finished. Kinda. A few more videos left. So now I want to talk about this in a little bit more detail. All right, so first off is the definition of an acid. And an acid means that it is a proton donor. So if I've got a solution and it's acidic, basically what that means is it's giving off protons. Well, protons are just another word for H+. And we have a probe, and it is measuring H+, but that's why we call it a pH probe. So let's pretend for a minute that this probe has been submerged into an acid solution, acidic. What that means is that this solution, it's like a big old wad of tobacco juice, and it's spitting it out. Pew, 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 pew. I mean, hydrogens are going everywhere. There's so many of them. That's the definition of an acid. Proton donor. All right, so if all of these hydrogens are out there in solution, there's quite a bit of them, right? So these hydrogens are coming in contact with that sol gel layer, that jelly little material that's a little lattice network that's got all these little openings in condos and high-rise apartments for $3,000 a month, remember? So these hydrogens are going to start making their way to the surface of that sol gel layer because there's quite a few of them, and why not? So the sol gel layer on the outside of this probe begins to get surrounded by the zombie apocalypse. And that zombie apocalypse is trying to make their way in to eat all the brains. And those brains, no, let's not go down that route. But that is a barrier. And the hydrogens are making their way to that sol gel layer. And it's going to start loading up on this side. Okay, well, what about on the other side of the gate? What about the other side of the fence? What's going on over there? Well, keep in mind, this is the ISE probe, and the ISE probe has hydrochloric acid in it with silver and chloride, right? We've got this silver electrode that comes in. It's in terms of a wire, but there's silver chloride in solution, and it's broken up by HCl. HCl, there we go. So that HCl also has some protons that are on this side of the fence, and that's fine. But the thing here is that it's held constant. So there are protons that will probably be on the inner workings of this wall, and that's perfectly okay, because why not? If that's the purpose of the sol gel, then that's what's going on. So if we put this probe into an acid solution, what we now have done is that we have exposed one side of that sol gel layer to a lot of hydrogen. And, you know, this is kind of porous. I mean, we talked about the structure of glass. We said that there was openings on the inside. That sol gel layer is a really tacky material that's here on the outside and the inside of this stuff. I mean, you know, things can freely kind of come and go in a way if they want. Now, the hydrogens don't go all the way across the glass structure, but it sticks to the surface. And folks, that's all that matters. It's sticking to the surface. That's good enough. So on the inside of the chamber, on the ion selective electrode, on the inside of this, we have hydrogen that's sticking to the surface. And you know, not too much stuff is going on here. On a normal day, on a normal time, during the work day, it's not a big deal. It's predictable. But then when we submerge this probe down into an acid solution, all of these hydrogens begin to migrate to the surface of that probe that we just placed in our solution. And there is a big charge distribution that begins to happen. I mean, if you kind of look at what I've done, and we'll keep it simplistic in a way, I've drew 1 and 2 and 3 and 4. I've put 4 hydrogens on the inside surface here attached to this jelly material, right? I mean, I'm just making these numbers up, but it gives you kind of an idea of what's going on. And then on the outside surface, I've went 1 and 2 and 3 and 4 and 5. So there's actually 5 hydrogens out here. Well, there's more. There's more positive on this side than there is on the inside of the probe. That is a charge distribution difference. That's what this is all about. There's more charge on the outside in terms of positive than there is on the inside. Okay, now hopefully you kind of see the road that I'm going down. So what happens here with this solution and what happens with this electrode is that they help counterbalance this. You know, the outside wants to match the inside. It sees it and it can kind of match it, but they do want to match in some form or fashion. So where's the extra H's coming from? Where are these extra positives going to be coming from, right? Well, this is acid, and there's tons of H plus that are kind of swimming around here, right? So these send out an alert, and it says, hey, inside of the probe, I need an extra hydrogen, man up, get me to the gate, please. So this extra hydrogen makes its way to the inside surface, and we see some movement that begins to happen. But when we do that, we've got these chlorides that are swimming around in solution as well, right? And these were counterbalanced. I mean, everything's consistent, everything is constant. For every hydrogen, there's a chlorine. I mean, that's kind of how this system is set up on the inside of that measuring probe. So when this hydrogen says, oh, hey, chlorine, listen, it was good hanging out with you, but I gotta go. I've been called into work. See you later. Well, that hydrogen migrates, and we see a negative that is now somewhat freed up. And this side of the probe does not like that. And this side of the probe says, whoa, 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 wait a minute. Now there's a chlorine that doesn't have a partner. That chlorine is single and it's carrying around a negative charge. Negative charges means they'll go crazy. Watch out for them. Watch out behind your back. Don't make them mad. They'll come after you in the middle of the night. So to prevent that from happening, this electrode says, you know, hey, listen, I'm made of silver. And that silver is going to be like, well, okay, I need to kind of swoop in here. I need to do the job that this hydrogen was doing in a way. So this silver is going to break down. And this silver actually makes some products. And that product is Ag+, and it makes an electron. And this Ag+ goes, ta-da! Hey, I'm positive. Chlorine, you're negative. We're going to get along great. So use me as the substitute boyfriend or the substitute girlfriend while your real one is away. And we get this electron, and this electron is created as a product. And guess what? Pew! That electron goes up the wire, and we get some voltage. That's somewhat what goes on inside of the ISE, or measuring probe. So what has just happened here is the process of losing an electron. And we've lost an electron in order to get that chlorine a little happier on the inside of that probe. So by losing electrons, guess what? Leo goes grrr. So this is loss of electrons, is oxidation. So this is what goes on in an acidic solution. Now, this difference, this distribution, the charge differences between what it was initially to what it is now, this is going to be in direct relationship to the electrons, aka voltage. We haven't made it quite there yet, but we're getting ready to make a step in that direction. All right, well, let's talk about a base, right? What is a base? How is this any different? Well, you learn it once, it's going to be the same stuff all over again. So here we get the inside of the ISE, and this time I've got a basic solution. And a basic solution most of the time is going to be a proton acceptor. That means it loves little protons, and it will go out and it will grab every little proton that it can see on the street and hop it into the back of its van and drive off. What kind of movies have I been watching? So if it sees a proton acceptor, or if it sees a proton, it's going to accept that proton, and it gives it a nice little home. So what will happen here is the same story as what it was before. We still get this sol gel layer, and this sol gel layer is still going to have these hydrogens that are going to hang out on the inside of it. And for the most part, this thing is meant to be consistent. It's meant to be the same. If nothing is going on weird at the surface of the gate or the fence or the barricade, then everything's going to be quite okay. And we get this pH of somewhat neutral, right? So now we've dunked that probe into a base. And sometimes we'll use this word alkaline, a alkaline solution. And that means that this solution's going around and it's freeing and it's taking up any of these free protons and it captures them. So what will happen here is that we might not have as many protons in our solution that this thing is finding and that this thing can measure. The thing is still operating the same way. Again, you learn it once, that's all you got to do. So there's the sticky stuff that the hydrogen is going to attach to, and there's the sticky stuff that the hydrogen is going to be attaching to. So no big deal. It's just two hydrogens on the outside. We've got a little bit more on the inside, and that's okay. Not a big deal. This sol-gel layer is still porous. The sol-gel layer still sees this hydrogen differential between the inside and the outside. And, you know, they kind of want to keep it the same. Whatever. It's the same thing as we just discussed. So what happens is that the hydrogen says, oh, you don't need me at work anymore? You want me to go home early on my shift? Okay, I'll do that. You don't have to ask me twice. So this hydrogen, and there we go. And now they match on both sides. Now, the problem is that we still have an electrode in here, and that is still in solution. So what we've done now is that we have added a proton, an extra proton in solution that was taken up just a second ago. And maybe one over here on this side too. Whatever, it doesn't matter. They just need to match. Tons of them will go on, not just ones or twos or fours or fives. This is just an example. So we've got extra proton that now has been released from the inside of this layer. And those extra protons make their way into the solution that this probe is into. Now keep in mind, this is still H and it's still chloride. Now, that is coming from the solution that is filled within the inside of the ISE. We've got HCl that's there. But folks, you know, we also have AgCl that's been dissolved too. And that's also present. So all of these extra hydrogens, it needs the other opportunity. All of these extra hydrogens that have now been dumped into that solution need to be killed out. And they need to be killed out with extra negatives. And those extra negatives can be in terms of the chloride. So this thing can give more chlorides off and say, yep, there you go. Sure enough, don't need to hang out with silver anymore. There you go. So this frees up silver, but that silver carries a positive charge. It's Ag plus and Cl minus. Now that chlorine that it was bonded to, that it was in a relationship with, just took off. Just took off and left it stranded. And that silver's like, what am I going to do now? I mean, you left me alone. I've got this positive charge. I'm not very happy. I mean, you took off and you got to that hydrogen because there were extras of them. We've just now in total have extra positives. Maybe you'll come back to me. And it could bounce back and forth. Chlorine's kind of shifty that way. I mean, it'll go hang out with hydrogen for a bit, and then it might go hang out with silver for a bit and be like, I'm tired of you again. And then it might go hang out with those extra hydrogens a bit. We get this change, right? And silver some point in time is going to be like, whatever. You know, we need to make sure that we put a stop to this. So that silver, if it could bind up to an electron, will neutralize the charge that it carries. And it doesn't need the cheater chlorine anymore. It's going to look at chlorine the next time it comes a knocking, and it's going to be like, you know what? You need to go on home. There's no room for you here anymore. You go have a happy life with your new hydrogen. And away it goes, because silver has now been satisfied. And silver has been satisfied with a little bitty electron that came around. This could be like a little puppy dog or a little kitten that made it happy. It doesn't need anybody. That's all the partner it needs in life. So if we do this, this creates neutral silver, and that somewhat kind of goes back to the silver electrode that is inside of the probe. Well, look at what we just did. We took silver plus, and we're like, listen, there's an electron out there. That electron had to come from somewhere, and it does. This is a galvanic cell. And that electron is going to attach to that silver atom, and it gets somewhat redeposited back onto the surface of the electrode. And this is Leo goes grrr, right? So this is gaining an electron. And when we gain an electron, folks, the process that's happening here, well, that's reduction. Gaining electrons are reductions. So that also has a voltage that's associated with it. That change, that electron movement, is it leaving or is it gaining electrons? What's going on? These are all directly voltage related. So depending on what's happening here, that is directly dependent on what's happening on the inside here. And that is dependent on what's happening on the outside of that probe. And that is how the probe works. Ta-da! I know that's clear as mud. Well, the bigger story here is that there's voltage, there's electrons, there's movement that's going on, depending if I'm in an acid, depending on if I'm in a base, what's going on inside of that reference cell and that measuring cell. Because keep in mind, the reference cell we've not talked about because it's not actually measuring anything. It's a reference cell. This is kind of its way of saying, okay, this is me, and double check, making sure that I'm working the proper way. That's what the purpose of the reference cell is. So what's happening here is that we're generating voltage. This voltage, that potential difference, the charge distribution, that is what we are focused on. That charge distribution is a voltage change. And that voltage change, folks, actually is very tiny. And this is a millivolt voltage change that begins to get generated and released through the wires that go into the meter. Again, galvanic cell. Electrons leave, go through the current, voltage is getting created. Or the other way, but it's millivolts. That's how tiny of a charge that this is going to be. So keep in mind that, like batteries that you put into the back of your calculator or to your TV remotes, those are volts. Your car battery, that is a volt. Those are a whole number of voltages. This is going to be fractions of a volt. Very, very super tiny. Millivolts. And the way that the millivolts is ordered is based on pH values. So here's pH of 7. If my solution is pH of 7, then that means the inside of the probe matches the outside of the probe. There is no hydrogens that leave and go home. There's no hydrogens that are called into work. So because of that, our millivolt difference is 0. Now we can define acids in terms of pHs. So the lower the pH, the more acidic we get. The more acidic that we get, the more hydrogens are freed up in solution on the outside. The more hydrogens that are freed up on the outside of that probe, well, the more hydrogens that have to be called in to work to make it match the inside of the probe. The more of those that have to be called in to work, the more negatives that have to be counterbalanced on the inside of that measuring probe. So the more electrons that that thing begins to generate. So what happens here is that this is going to be 59 millivolts. And then another pH value, when we go to pH of 5, that's another 59. We go to another pH of 4, that's another 59. Then we go to 3 and 2 and 1 and pH of 0 and on and on and on and on and on. Every time we go into a different pH whole number, 6, 5, 4, 3, 2, 1, we gain another 59 millivolts in the electron flow. And this meter is looking at the millivolts that this thing is starting to create, and it's looking at that readout, and it's corresponding that to a pH value that is on this scale. The same thing happens to the base category. The base category, okay, I put it in a solution. There's not a lot of hydrogens there. right? So the inside surface of that probe says, hey, listen, we got too many hydrogens that are at work right now, so go home, we don't need you. So extra hydrogens begin to leave the surface of the inside cell. It begins to make an imbalance on the inside. There's more positive now than there are negatives. Those positives are counteracted by extra electrons that these things begin to suck up, and it starts sucking electrons in. Again, a charge distribution. That creates a voltage, but that voltage is going the opposite way. We are gaining that. We have to have electrons in order for that to work. So the same deal here. It's still 1 unit apiece. pH of 8, pH of 9, pH of 10, pH of 11, pH of 12. And every time we go to the next whole number, we are seeing another change of 59 volt, 59 volt, 59 volt, 59 volt, 59 volt. They just keep adding on top of each other, except it goes in the opposite way. So the acids are generating a positive voltage, and the bases are generating a negative voltage. It requires electrons in order for that to work. On the acid side of the house, it doesn't need those. It's spitting electrons out. If it's spitting electrons out, then those electrons are free and they can go up through the wire and generate some voltage. But if we're on the base side of the house, it requires those electrons. So it's going to take those electrons from somewhere, aka reference probes in the inner workings of the ISE, and it needs them, it eats them, and we require it, which makes that voltage go down negative-wise. Folks, I'm going to say 59 on this screen, but the actual number here is 59.16 millivolts. That's the actual value. That's how many millivolts it takes to change a pH number, whether it goes more acidic or whether it goes more basic. Whew, what a doozy. So in the next video, we're going to talk more about the voltage now that we've made it to that point, and we're going to talk about how we can ensure that this meter is calibrated the proper way, because it will go wonky. And as a user, we have to calibrate these things very, very often. And so how does that actually do its job? Well, I think that you can kind of expect now that it does its job by looking at millivoltage. So for instance, if I have a solution that has a pH of 4, I should be generating a millivolt of 177. Is it? Think of it like a calibration weight. If I have a calibration weight of 20 and I put it on the balance, is it really 20? And the same thing's going to happen here with a pH meter. If I have a buffer 4 and I put that probe into that buffer, is it generating 177 millivolts? Because by definition, that is what should be getting created. And that's what we'll talk about in a little more detail in the upcoming video. Don't stop here. You're on a roll. Come back, hit play for the next. It's like the sequel. You can't wait.